Hello everyone, this is Dr. E, and for today we're going to learn how to classify triangles and use theorems and corollaries to solve the angle measurements of a triangle. We have worked with a lot of geometric figures, and one of the most popular geometric figure in geometry is a triangle. And we're going to be diving into more detailed theorems and corollaries that we'll be able to use to be able to solve for problems involving triangles. So let's start, of course, with the formal definition of a triangle, because we know that triangles are just a geometric figure with three sides and three corners. But if we're going to dive deeper into how we are understanding triangle according to geometry or geometry language, first we're going to define it as a geometric figure that is formed by three non-collinear points connected by segments. And we are seeing three non-collinear points here, E, B, and A, and they're non-collinear because we're seeing that they're not linear and they're not on a line, and we are able to connect the dots and create a triangle from these three non-collinear points. Another way of describing a triangle in geometry is that the non-collinear points are called vertices. And singular form, of course, is a vertex. So these points right here, EBA, we call it vertices, and we can write our triangle from the corners or from the vertices that we are seeing. It could be triangle EBA, ABE, or BEA, as long as those letters are in that triangle, then we are referring to the correct triangle that we are looking at in our diagram. And lastly, the segment joining the points of this triangle, we call them sides. So if we connect those dots together, we call those parts of our triangle as its sides. So this is our triangle. Now let's use it to identify the parts of a given triangle. So let's say we have triangle PQR, and we're going to identify which angle is opposite segment PQ. So first we need to identify PQ so that we can answer the first problem, which is from triangle PQR. This is side PQ, and the angle opposite it is angle R. So we'll write angle R for problem number 1, which is the angle opposite to the line segment PQ. Now notice that in geometry, notation is important, so make sure that you know how to write symbols associated with the description of the geometric figure or parts that we are working on. So let's have the problem number 2, and for problem number 2, we need to find the side that is opposite angle Q. This is angle Q, and this side is opposite angle Q, so we are naming it PR, or line segment PR, because this is the side that is opposite angle Q. So knowing your notations and knowing your description will greatly help you understand geometry. So for problem number 3, if we're going to look for which side is included between angle P and angle R, so we know that angle P is here and angle R is there, and the side that is included in between those two angles will be side PR. So this is how we use our parts and how we use notations in geometry to name our parts in a triangle. So we have a triangle, and since a triangle is a very popular shape in geometry lesson, we have different types of classification for triangles according to its angles and according to its sides. Let's start with how to classify it according to its angle. So in this diagram, you are seeing an acute triangle, and by definition, it means that all three angles in this triangle are less than 90 degrees. And if we have an acute triangle, we also have an obtuse triangle, wherein we have only one angle that is over 90 degrees. And this is the obtuse angle that is obviously showing in our triangle. Therefore, we call this an obtuse triangle. And if we have an obtuse, we have acute, we also have equiangular. And equiangular, from the word itself, equal angle, which means all angles are equal. However, there's a caveat here because we need to make sure that we are using the correct symbols to denote that we are seeing congruent angles or angles with the same measurement in this triangle. So this symbol right here is very important to make sure that we are verifying that we are seeing an equiangular triangle in our diagram. Next one is the right triangle, and in this particular case, we cannot classify this yet as a right triangle because we need to show a right angle symbol in our triangle, and this is important because without the symbol, we really cannot verify if our triangle is indeed congruent or right or equiangular, just like what we have seen. So to summarize, how to classify the triangles by its angles, we have acute, obtuse, equiangular, and right triangle, and all this classification is specific to the angles of our triangle. And if we're going to classify our triangle according to its sides, we'll have this description over here, and we are going to use a different type of triangles because now we are focusing on its sides. So we are seeing the scalene, isosceles, and equilateral. And you will see that in our isosceles triangle, we are seeing the little symbol again, which means these two lines right here are congruent. And this equilateral triangle showing that the three sides that we are seeing are all the same. So we have the scalene with no equal sides, isosceles with at least two sides that are equal, and the equilateral wherein all the sides of the triangles are equal. Now, how are we going to use these classifications in triangles specific to this particular triangle that we are seeing here right now? We are seeing a triangle that is 90 degrees and that their sides are not equal. So according to the angles, we classify this as a right triangle, and according to its sides, we call it scalene triangle. So its complete name, therefore, we can call it now as right scalene triangle. So this is how we use the classification of our triangle according to its angles and sides. So if we see a triangle similar to this one, we're seeing that all of these angles are less than 90 degrees, and there's no right or obtuse angle in our triangle, so we can call this as an acute triangle. And according to its sides, we're seeing the two markings again, and these two markings denote that we have two equal sides, so we can call this isosceles, and its complete name now, we can call it as acute isosceles triangle. So that's how we use our classification for these triangles, which is very helpful when we are working and understanding theorems in geometry, even corollary and postulates, where we use geometry language when we're working with definitions and descriptions of this theorem. So understanding how we name it is going to be beneficial for us to understand geometry better. Now let's have the first theorem of the day. We call it Triangle Angle-Sum Theorem, and Triangle Angle-Sum Theorem, it states that if we add all the interior angles of our triangle, it will equal to 180 degrees. And that is basically our triangle angle sum theorem. And if we're going to use geometry or geometric notation to denote that this theorem exists, all we need to do is to add angle 1, angle 2, and angle 3 equal to 180 degrees. Now let's try to prove it using this triangle right here. So according to the triangle angle sum theorem, the sum of angle 1, angle 2, and angle 3 is going to equal to 180 degrees, and we know that 180 degrees is basically a straight line. So a straight line is 180 degrees, and if we add these three angles together, we'll be able to form a straight line. So how are we going to show that using our triangle? So let's cut the corners, and let's see if we can create a straight line by combining all this triangle right here. So to do that, let's move our angles around, and we are seeing a straight line that is forming from angle 1, 2, and 3, which is a 180-degree angle. So from our triangle right here, or the piece of our triangle without the corners, we're able to produce 180 degrees, which shows us that if we add angle 1, 2, and 3, it's indeed equal to 180 degrees, which is our theorem in this particular triangle. And if we have theorem for our triangle, we can also produce other descriptions that will help us find the angle measurement of a triangle. The first one is the exterior angle of a triangle. And according to this, if we add the two angles in the interior part of our triangle, if we extend one of its sides, this angle measure right here is equal to the sum of these two angles. So this is basically the exterior angle of a triangle. The measure of each exterior angle of a triangle equals the sum of the measures of its two non-adjacent interior angles. And we call this a corollary, and a corollary is another term that we use in many geometric theorems or many geometric lessons that we are working on. And by definition, a corollary is a special name that we give to a theorem that is easy to prove as a direct result of another previously proved theorem. So we're able to prove this particular theorem in our triangle. Now we have corollary, which is a theorem that is easy to prove because of the theorem that we have previously proved from the first theorem that we have. So remember that if we want to find the measure of this angle, all we need to do is to add the two non-adjacent interior angles, and that will give us the measurement of this exterior angle. And another theorem that we are going to be using is the acute angles of a right triangle, which means the two acute angles of a right triangle are complementary, which means if we add these two together, it will equal to 90 degrees. So instead of using 90 degrees, notice that we use complementary because we need to understand that we need to know the words associated to these terms in geometry so that we'll be able to understand what we are reading in a mathematical theorem similar to this one. And this is another corollary coming from the Triangle Angle-Sum Theorem, or the theorem that we have done a while ago. So if we add angle 1 and angle 2, it's equal to 90 degrees, which also proves that if we add these three together, it will equal to 180 degrees because 90 degrees plus 90 degrees is equal to 180 degrees. So now let's use these theorems in answering problems similar to this one. We are using the Triangle Angle-Sum Theorem to find the measure of each angle in this given triangle. So we are not given measurements or exact measurements. We are given algebraic description. So let's use algebra then to be able to solve the sides or the corners of our triangle. So we have measurement of angle 1. If we add it to measurement of angle 2, and if we add it to measurement of angle 3, it will equal to 180 degrees according to the Triangle Angle-Sum Theorem. But in this case, 1, 2, and 3 are being shown as an algebraic expressions. So for angle 1, let's name it, or let's use 5x degrees for angle 1, and for angle 2, 6x degrees, and for angle 3, 15x plus 24 degrees, which is equal to 180 degrees. And now we are seeing an algebraic equation. So by combining like terms, we're going to add this, this, and this will give us 26x plus 24 degrees equals 180 degrees. And by subtracting 24 on both sides, we'll cancel this and we'll have 26x equal to 156. And by dividing both sides by 26, x is equal to 6. So now all we need to do is to use the value of x so that we can find the measurement of this corner this corner, and this corner. Since we are able to use our theorem and algebra together, we can now completely solve our problem, knowing that 5x is the same as 5 times 6 because x is equal to 6. So we have 30 degrees, 36 degrees, and the last corner is going to equal to 114 degrees by substituting the value of x in our expression. And if we want to check if our calculation is correct, we know that if we add 30, 36, and 114, it should equal to 180 degrees, which is true in our solution. So this is how we use the theorem and algebra to solve for the missing angles of our triangle. So let's use another theorem, and this time we're going to use the exterior angle of a triangle corollary to find the missing angles that we have here. So we have one exterior angle and one interior angle in our triangle, and we'll be able to solve this because we know from our corollary that all we need to do is to add these two angles, and this will equal to this angle that we have here from our corollary from our previous lesson. So all we have to do is now to write our equation, which is the most challenging part in every geometry problem. So our equation, it says here that if we add x degrees plus 67 degrees, it will equal to 3x minus 53 degrees. So now that we have an algebraic equation, all we need to do is to combine like terms. What we can do is to combine the x's, combine the constant, and by doing so, we'll be able to find the value of x. So from 3x minus 53 equal to x plus 67, we can subtract x here, and we can add 53 degrees here, and we'll be able to have 2x minus 3 is equal to 67, or 2x is equal to 120. So we'll have x is equal to 60 degrees as the measurement of our angle x. So now, all we need to do is to plug in the value of x to our expression. So this corner right here, it's equal to 60 degrees. And if we're going to find the measurement of this exterior angle, it will be 3 times 60 minus 53 degrees, which is equal to 127 degrees. So that's how we use our theorem to be able to find the missing angles of our triangle. So for your number bender challenge of the day, now that you know our theorems and its corollaries, how are you going to figure out the measurement of angle 1, 2, and 3 from this diagram? Comment it down below, and let's see if you'll be able to figure out a way on how to solve these missing angles. And this is our lesson in mathematics, or specifically in geometry. And in working with problems involving geometry, we need to be familiar with the symbols, notations, theorems, and how we write things in geometry, so that we'll be able to understand how the calculations works in a geometric problem similar to what we have today. This is Dr. E, and see you again next time. Bye!